also has stuff from the homework for this tonight. So maybe what we could do is midway through class, I could give you the quiz just as an activity, as a sort of, so when we get to the point where it makes sense. And then I'll get you a new quiz for Friday, so it'll be fine. The first question is similar. You should be able to do the first one, but there's this second question. So we'll save that for just a bit. Okay, so let's take a look at, wow, I can hardly see this screen. Just a minute. Turn the brightness up. Okay, so I want to remind you of what a Laplace transform is. So the Laplace transform, it's just the top there. That's the important one, this one. That's the one that we're going to rely on. But as I mentioned earlier, once you've done the Laplace transform for a function, there's no reason to do it again. So you could think of it this way, that mathematicians have done this for you so that you don't have to. And so maybe we'll do one or two more by hand, but then we'll take a look at the table and then see how we can use the table to make things more efficient. So let's do the Laplace transform for the sine. So the sine of t. This is going to be fun. I can feel it. So give me a sec. I'm going to switch over to Notability because that's going to be a lot easier to work with. So hold on just a minute. You can get started, though, by setting up the Laplace transform for the sine function. Copy and delete, switch over. Whoa, where's my Notability? There it is. Okay, paste it in there. Okay, so you're probably really excited about this because you can see what's going to happen is that the Laplace transform for the sine is going to be an integral of the exponential function times the sine function. What could be better than doing integration by parts? I don't know, so I'm just going to do it. So what we'll do is we have to pick one of these to be u and dv. Yeah, this is an integration by parts thing, sorry. So we're going to have a u and we're going to have a dv. I'll let you choose. Just a minute. But we want to be consistent, so I'll let one of you choose. Pick a random student. Mariah, do you have a choice as to which of those two? Yeah, product. By the way, the reason why I'm using integration by parts is because you have a product, and anytime you have a product, you want to use the reverse of the product rule, which is integration by parts. So you have to pick a u and you have to pick a dv between those two. Which one do you want? For u? Let me pick another person. Okay, Tyler, which would you like to have u? Are you guys ganging up on me? Matthew, do you have a choice for you? Okay, I lied. I am not going to let you choose. Okay, Cooper. No. Okay, so I should say it really doesn't matter, but there is one that's easier than the other. You could use either, you could go either way. If you use sine for u, it means dv has to be e to the negative st. My goodness, what's wrong with you people? I gave you a chance. Okay, so anyway, so dv is equal to sine of t dt. There. Okay, now we're all with the program. I know, I lied. I wasn't really going to give you a choice. I just thought you'd figure it out. Oh, look, randomly chosen, Cooper Stiegel. What's the derivative of e to the negative st? Very nice. Times dt. Good job. And then we need the antiderivative of sine. And Rachel J., you know the antiderivative of sine, don't you? Beautiful, negative cosine. Okay, so we're using integration by parts. And so this thing becomes, let's see, this is the integral of u dv is equal to uv minus the integral of v du. Okay, so let's put it all together. Let's see, this is going to be u times v negative cosine times e to the negative st. So that's, I know, I just did it backwards. I don't know why. That was dumb, but whatever. It's a product. You can multiply. It's a commutative. Okay, so we've got that. And then we're going to subtract the integral of v du. There's going to be a triple negative here. Let's see. So this is going to be v du. Let's see. I'm going to just do this. Cosine of t e to the negative st dt. Okay, so far so good? Now, here's the trick. Whenever you're doing integration by parts, if you find that you have to do integration by parts more than once, you have to use the same functions. That is to say, I have the exponential that I guess I chose. I was hoping one of you would choose it, but you didn't. The exponential is my u, and my dv is the sine, so it'll be cosine on this second go round. So the reason why I'm so insistent on using u is equal to this is because if I had dv equal to that, then I'd have to have a bunch of fractions lying around. I don't like fractions if I can avoid them. So this just avoids the fractions. So let's do integration by parts the second time. So u is equal to e to the negative st, and dv is equal to s times the cosine of t dt. That's an s, not a 5. Okay, so then du, I think you told me, I'll just believe you, negative s e to the negative st dt, and then v is equal to sine, s times sine. Wow, it looks like sine, okay, of t. Okay, we're almost there. Okay, so this, now we have this equals negative cosine of t e to the negative st. That's just this right here. And then, here it goes, u times v. So this is our second go. So u times v is going to be s times sine of t times e to the negative st. That's u times v. I know, v times u, close enough. Minus the integral of v du. But notice because you've got a negative in here, we're going to double negative and get a plus. Integral of v du, so this will be s squared. What am I doing here? Sorry, e to the negative st sine t dt. Okay, let me clean this up just a bit. Just give me a sec, because there's a lot going on here. We aren't going to do integration by parts again. Trust me, we're all done. So this is negative cosine e to the negative st minus s times the sine e to the negative st minus s squared times the integral of e to the negative st sine of t dt. Okay, so that's where we're at. All I've done here is I've kind of expanded. I've multiplied through by negative. I think everything's good. Now here's the interesting thing. Welcome back. I hope you crushed it. We're just suffering through some integration by parts. We're almost done, and by the time we get done, no one's going to care. So yeah, trust me, you're not going to care once we're done. Whoa, I didn't mean to do that. Hold on a sec. Can I get rid of? Apparently not. Okay. Here, I'm just going to slide this over so we don't have to look at all that extra stuff. Whoa, that was weird. Guess I can't slide it over. Okay. So anyway, so here's the deal with this. You might notice that you have an integral of e to the negative st on this side. You have an integral of e to the negative st, or sine of t on this side. They're both the same. So let's combine them on the right or the left side so that this is one of them right here. Here there's one of them. This one is multiplied by s squared. So that's an s squared times this. That one's one of them. So when I combine them over on the left side, I'm going to have 1 plus s squared times that. So it's going to be 1 plus s squared times the integral from 0 to infinity of e to the negative st sine of t dt is equal to this stuff right here. So let's see if I can sort this out. E to the negative st times the quantity negative cosine of t minus s times the sine of t. Well, you probably can guess what's going to happen is I'm going to divide both sides by that. I'm almost there. And thank you for enduring. This is like one of those moments where I get to pretend to be a mathematician and you're just humoring me. Because like I said, seriously, when we get done with this, you're not gonna care about anything but the final answer, and that's fine. I'm okay with that. Okay, so there it is. So let's actually evaluate this from 0 to infinity, and then we'll be all set. So remember, these are values for t. T goes from 0 to infinity. The upper limit, infinity, I think you can guess what's going to happen, that because of this, the cosine and sine are always between 0 and 1, or negative 1 and 1. And so those, there should be an s somewhere, shouldn't there? There should be an s. There it is. The s is right there before the sine. There. S, that's s times sine. So the sine and cosine are all between negative 1 and 1. This, though, when you do the limit as t approaches infinity, as long as s is big enough, remember this idea that we can just choose that s is always bigger than 10 or something, then this will limit as t approaches infinity of this is 0. So the limit as t approaches infinity of this whole thing is 0. So we've got this equals to 0 minus what you get when you plug 0 into here for t. And notice what you get when you plug 0 in for t is this will be 1. I'll write it out. 1 times negative 1 minus 0 over 1 plus s squared. And lo and behold, this is the final answer. So all of that work, look at it all. Yeah, you're glad that you came late, right? So all of that work was in service of showing that the Laplace transform of the sine is equal to 1 over 1 plus s squared. Whew. So much work. But here's the cool thing. Now that we've done it, we will never do that one again. In fact, actually, we will never do a bunch of them again. There's a few that we still need to do. But these, I'll show you the ones that we don't need to do, and then I'll give you the quiz. The ones that we don't need to do are found in this table right here. This table is found in your book. I don't know where. It's labeled Theorem 7.1.1. You're going to be practicing this. In fact, I'm going to have you practice it on this quiz. Yeah, those who just got here. The quiz, I had prepared a quiz. Actually, I pulled it out of my files. I printed it, and then I realized, oh, yeah, that should be given like in the middle of class. So we'll do it as sort of an exercise in just a minute that I won't collect. But anyway, notice that sine, where did the sine go? Here it is. Sine, the Laplace transform of sine of t, ignore the k for a minute, k is 1 if you have sine of t, is 1 over s squared plus 1. Now let's say you do sine of 2t, then the Laplace transform, we could go back and do it, but I don't think anyone wants to. The Laplace transform of sine of 2t is 2 over s squared plus 4. The Laplace transform of sine of 3t is 3 over s squared plus 9. I think you probably are getting a pattern here. And so each one of these have been done for you. We've already talked about this. In fact, let's actually employ this, and then we'll do the quiz here. Let's see, what's this? There's a bunch of stuff there. Yeah, let's ignore that stuff at the bottom. Let's stick with this. Let's stick with this stuff. So let's just for fun, we'll do the Laplace transform of something like, I don't know, 3t squared plus 2t plus e to the negative 5t, just to make it a little bit more interesting. So to do this Laplace transform, what we'll do is break it down into its individual parts, like little Lego bricks. You're like, well, what do we transform this into? So this is totally legal. It's totally legal to just focus on the actual functions that you're adding together. So I have the t squared, and I have e to the negative 5t. So those are the three building blocks I'm going to be working with. Let's put them together. So we have 3 times something, we'll get the something in a minute, plus 2 times something else, plus the last thing. So we'll do the first thing is that t squared. So where is t squared? T squared fits into this category. And in this case, the square that's n is equal to 2. And I think we did this one last time. So the Laplace transform of t squared is 2 factorial over s to the third. You're going to do this so often that, like with polynomials, that this will be, you'll have that part memorized. So you should have that memorized. Despite that fact, I think I actually have a table on the exam. So this is 2 factorial over t to the, or sorry, I get, oh no, I have to, oh well, it's all going away now. Start fresh. Okay, let's try again. 2 factorial over s cubed. Is that all right? So it's actually 2 over s cubed. And then let's do, so let me highlight that one. Highlight that. There's the yellow. Beautiful, isn't it? Now, the green, the highlighted green, you'll see is just t. That's t to the first power. T to the first power, that's 1 for n. So I'm going to do 1 factorial over s to the second. Well, that's easy. That's just going to be 1 over s squared. And then finally, the last one is the e to the negative 5t. Let me highlight. Highlight this one is the green one. And then e to the negative 5t fits into this category. I'll just highlight and hope for the best. Okay, so you can probably figure this out, that e to the negative 5t, a here is negative 5, so you have 1 over s plus 5. Ooh, why did I pick 5? I hate 5. Well, I hate s more, but I'm stuck with s because these are Laplace transforms. Okay, I'll try to make the s extra curvy and the 5 extra jagged. There. That's not bad, is it? There it is. So there it is. So the Laplace transform of this function on the left is this function on the right. Think of it as we're moving from where we measure time with t to measuring time with s. It's a different universe. We've gone into Narnia. And we're going to do some math, and then we're going to come back to the real world. By the way, I think you might be able to guess that despite the fact that this is going to help us with our differential equations, we're going to have to deal with fractions. There are a lot of fractions here, aren't there? Yeah, it's going to be ugly at times, but don't worry. Let's give this a go. See how we do with this. It says quiz, but you know, I'm not going to collect it because this is sort of a practice. So here's 2, here's 3. Let's do our best and see how we come out. And notice that I've got a table on the bottom. That table is the same table that will appear on your exam next week and any other thing. Like that's the one that I use. I'm just copy and paste it. I probably didn't give someone enough. 1, 2, 3, 4. And here's one more for Cooper in the back. Who needs one? You need one? No? You want one? All right, there you go. Who has an extra one? You've got an extra one? All right. I got it. Okay, so do your best. We'll regroup here in just a minute. I need to get this onto my notability so that you can all see the incredible joy that we're going to have. Weird. Let's try again. Let's see. Come on. All right, I'll give you another, I don't know, 30 seconds or so, and we'll see how we're doing. Okay, so for this first one, you'll have a problem like this on the exam, but there's a way around it because I know you don't want to do this. I don't want to do it either. So here's the trick, is you write down the integral like this so that you show me that you know what's going on. You know, it's going to be an integral from 0 to infinity. You got to throw an e to the negative st in there. And then you know what the answer is going to be. That's the thing. you already know the answer. Here, let me just show you. You know the answer because it's down at the bottom there. You see it? The answer is right here. Wait, where is it? Oh, it's not there. It's not. Oh, that's hilarious. Okay, well, it will be. It will be on the list because, you know, exponential function is kind of important. Okay, so here, I'll pretend it's there. Okay, e to the at is 1 over s minus a. Okay, so you're like, yeah, I already know the answer. It's going to be, wait, where's what is a? Oh, a is 3. So you know it's going to be 7 over s minus 3. That's the answer. So here's what you do. You put an equals sign down here, 7 over s minus 3. And then you just put something in between, which makes it look like you did your work. Okay, so here's the something that I might do is I'll say, okay, I can do a little bit of algebra. It can't be that hard, can it? So this is going to be 7 times e to the 3t minus st. And then, you know, we could just do a little bit more algebra. It's not that hard, is it? So this will be integral from 0 to infinity of 7 e to the 3 minus s times t dt. And then you might as well just do this, throw this in there just to make it look like you know what's going on. 3 minus s, 7e to the 3 minus s times t. Whoops, those should be in parentheses. Sorry about that. And this is evaluated from 0 to infinity. And then, yeah, okay, that works. Oh, this should be, yeah, because we know that s can be as big as we want it to be. And so as long as s is bigger than 3, this will be a negative exponent. And then when you do the limit as t approaches infinity of a negative times infinity, you get 0. And then you do the lower limit, and what happens is you get the negative of 7 over 3 minus s, which is the same as 7 over s minus 3. Okay, so maybe you want to fill in a little bit more than that, but that's pretty good, isn't it? So that's what you would do. Yeah, so on the actual exam, you'll have the full table. I don't know why I left that off, but maybe it was to force you to do the integral, but I don't care. Okay, so let's do the rest of these. The rest of these are pretty straightforward because you're just identifying the things that you're plugging in, substituting, so sine of 2t. And honestly, after you do this a few times, you actually start just having these memorized and you don't need to look at the table, but it's nice to have the table nonetheless. Say the polynomials especially, you're going to have those memorized after you do a few differential equations. So this one, cosine of 3t, is going to be s over s squared plus k squared. Oh, sorry, k is 3. So that's a 9. Plus, this will be 3 over s squared. So it's been a year since I've been doing. Wait, did he just leave? He just left? No, I knew he had a game. It's just I was hoping that we could all leave together. Well, no, we got to finish. Let's finish this at least. Come on. No, we got to make sure you got it right. I was thinking you could finish this, and then I'd be like, oh, you got to leave. Let's all go. And I thought it would be funny, but now it's not. Okay, I knew that he had a game. It would still be funny. Okay, okay. Onward. Okay, let's do this one. I guess I wasn't quick enough earlier. I thought he said 3. I didn't know it was 2:45. Oh well, whatever. Maybe he has to meet down there at 3. Is that the deal? Okay. So this one is going to be 6 over s to the 4th minus 6. No, not 6. 4. Sorry. 4 over s to the 3rd plus 1 over s. So here, once again, we're just comparing. So we're using that t to the n there. Oh, I guess I have t squared. Why do I have t squared? I don't know what I'm doing. But yeah, t squared is 2 over, so that's 2 over s cubed. So just, but it's pretty straightforward. If it's a polynomial, you always have one more power in the denominator with the s. So t cubed turns into s to the fourth, t squared turns into s cubed, t to the 0 turns into s, t to the 10th would be s to the 11th, and then in the numerator, you always put the factorial of whatever number is here. And that's because of the fact that if you were to do this using an integral, you'd end up using integration by parts and getting a factorial. But anyway, 6 here, and then this is 2 times 2, and then the 1. So excellent. Final one. And so we have sine of 3t, which ends up being 3 over s squared plus 9 minus the hyperbolic sine of 3t, which is 3 over s squared minus 9. Now, just a quick note, you're going to see a lot of hyperbolic sines and hyperbolic cosines. The reason for this is because it will save you from having to deal with more algebra. If you just, if we can handle the hyperbolic sines and cosines, it will save you from more algebra. So let me just mention what the hyperbolic sine and the hyperbolic cosine are, and then we can go and join Zechariah out on the soccer pitch. Wait, what do they call it? The lacrosse pitch? They call it a pitch? Maybe? Okay, we'll call it a field. I like pitch better. It just sounds exciting. Okay, so hyperbolic sine, here's the deal. Hyperbolic sine, just in case you don't know. Oh, cosine is the better one. Cosine, you're averaging together e to the t and e to the negative t. That's what the hyperbolic cosine is. This, by the way, is this so-called, or it's not so-called, it is a catenary. It is what you get if you suspend a cable or a rope from 2 points, you get a catenary. A self-supporting arch like the St. Louis arch is an upside-down catenary. So the hyperbolic cosine. Okay, so the hyperbolic sine is the same thing, only we have a minus there instead of a plus. There we go. So here's why you should be happy that we are using hyperbolic functions. It's because if we didn't, what we would have to do is we would have to take this thing and use partial fractions to do this. S minus 3 b over s plus 3, because you could factor the denominator and you would eventually get e to the t, e to the negative, well, in this case, e to the 3t and e to the negative 3t over 2. But we don't want to do that. We don't want to do it. And so it's much better if we can just use this hyperbolic sine as a stand-in for this. And same thing goes for the hyperbolic cosine. It'll save us work in the long run. Okay, I think you have plenty of stuff to be able to do your homework. Oh, no, you don't. Well, you do. Okay, let me just mention this. One more thing. Let's say, so here's, you might think, well, why do we even care? Here's why we care. Laplace transforms are great because if you have a discontinuous forcing function like this, or better yet, just a minute, I'll show you. Oh, this will be good. Here, I will show you a discontinuous forcing function. Hold on a minute. Come on. Okay, here. Yeah, we'll do this, and then we'll be all done. Okay, so there's a spring mass system. This is a hammer. Okay, pretend. There, discontinuous. Did you see it? Okay, yeah, so all of a sudden you have this shock wave that hits. That is a discontinuous forcing function that will affect this system. Anyway, if you have a discontinuous forcing function, which you can have, so like here, what you have is you have some impulse, and then it just drops off. Oh, here's another. We have a RLC circuit up there, discontinuous. It's a discontinuity. When I flip the switch, there's a discontinuity between on and off. So anyway, we care about things like this. Anyway, if you wanted to do the Laplace transform of something like that, you would have to actually, like here, this is 0, that's 0. And so the Laplace transform, let's just say that that's 1 there. The Laplace transform of this function ends up being the integral from 0 to 1 of e to the negative st times whatever this is, because this is 0 over here. So if you have a discontinuous function and it's only, so this is like, this is on, this is off. But anyway, you would do e to the negative, I guess this is just t, f of t equals t times t. So notice now I have a lower and upper limit that's not infinite. So there are a couple of discontinuous, you do your best with them. I know you just want to go watch the lacrosse players, so you can go join them now. But stick around if you want to chat. I'm going to stop the recording just in case